Right now, South Florida is flooding. The Sierra Nevada is about to disappear under 6 feet of snow. The Southwest is on fire weather alert with single-digit humidity. 14 Midwest rivers are above flood stage. And this weekend, a tornado outbreak begins across the central United States that forecasters are calling the worst severe weather setup in about a year. 5 emergencies, 1 country, 1 connected atmospheric system driving all of them simultaneously. That is not a coincidence, and it's not random bad luck. It traces back to something building beneath the Pacific Ocean that hasn't fully arrived yet. Stay with me, because understanding what is coming will completely change how you read every weather story for the rest of this year. If you are new here, hit like and subscribe, because this story is only beginning. The double barrel low is still spinning up. The moisture is still surging north. The 5 emergencies are still converging. None of it has resolved yet. This channel breaks down exactly what the atmosphere is doing and why it matters. And we are not stopping until this pattern plays out. We will be here for every round, every update, every piece of this that the nightly news skips over. You will want to be here too. Now, let us get into it. There is a moment in meteorology when the noise stops and everything goes quiet, not because the atmosphere is calm, but because every single forecasting system on the planet is suddenly pointing at the same thing. That moment happened this week. And if you've been following severe weather long enough to understand what it means when independent forecasters stop disagreeing, then you already feel what I'm about to describe. The Storm Prediction Center, the federal agency responsible for issuing severe weather outlooks across the continental United States, published something unusual in their extended forecast range. 4 consecutive days, days 4 through 7, all of them flagged with a 15% severe weather probability. Now I know that number sounds modest. 15% doesn't exactly inspire panic. But here's what that number actually means, in context, because context is everything when we're talking about the atmosphere. Days 4 through 7 in a forecast cycle represent the low confidence zone. Meteorologists call it the extended range for a reason. The further out you go, the more the atmosphere blurs. Chaotic systems compound their uncertainty. Small errors in initial conditions snowball into wildly different outcomes. The standard practice is to issue general mentions, vague hatched areas, cautionary language with heavy caveats. You do not, under normal circumstances, light up 4 consecutive days in the extended range with consistent severe probability highlights. The fact that the Storm Prediction Center did exactly that is not a bureaucratic footnote. It is a signal. It means the atmospheric pattern is so clearly organized, so well defined in the data, that even at low confidence range, the signal overwhelms the noise. The atmosphere is essentially screaming at the models, and the models are screaming back. But here's where it gets genuinely remarkable. The Storm Prediction Center didn't make that call in isolation. Max Velocity Weather, one of the most respected independent meteorology voices in the country, looked at the same data and called this the worst severe weather setup in about a year. Ryan Hall Y'all, whose audience of millions tracks every word he says during major setups, independently called it one of the biggest setups of the entire year. 2 separate forecasters, using different model weighting systems, operating with different internal thresholds for what qualifies as significant, and they landed in essentially the same place at essentially the same time. In the scientific community, there's an informal concept for when this happens. Think of it as a consensus compression event. The moment when forecast spread, which is normally wide and messy and full of disagreement, collapses inward like a closing fist. The ensemble models, which run dozens of slightly different versions of the atmosphere to capture uncertainty, stop showing a cloud of possible futures and start converging on a single storyline. When that happens at days 4 through 7, experienced forecasters pay attention. Very close attention. Now, I want to be precise about something, because precision matters here, and the internet tends to turn weather forecasts into catastrophe theater. What this consensus compression event confirms is not that tornadoes will hit your specific town. What it confirms is environmental readiness, that the atmosphere is building an architecture capable of producing violent weather across a large area over a multi-day period. The difference between those two statements is the difference between understanding meteorology and panicking at a headline. The ingredients are assembling. The question of what gets cooked depends on execution, and execution depends on variables that resolve much closer to the event. But here's the open question that should be sitting in the back of your mind right now. Why are all these independent systems seeing the same atmospheric fingerprint at the same time, when forecasters almost never agree this far in advance? What is it about this particular setup that is so clearly written in the data that it refuses to be interpreted any other way? The answer starts with the structure of the storm system itself, and it's not what a typical severe weather pattern looks like. Most significant severe weather events in the central United States are driven by a single, well-organized low-pressure system tracking northeast across the plains. You get your warm sector, your dry line, your cold front, your squall line, your tornado corridor. It's a formula. Forecasters know the formula well. What is approaching this weekend does not fit the formula cleanly, and that is precisely what makes it so consequential. What the models are showing is a double-barrel low structure, two separate low-pressure centers interacting across a large area of the country. Think of it this way. Imagine a car engine running at full throttle. Now imagine that as that engine starts to sputter and die, a second engine ignites just behind it, running off the same fuel. The first low-pressure system develops over the Central Plains, organizes severe weather, begins to weaken and occlude. That's the meteorological term for when a low-pressure system gets cut off from its energy source. In a normal setup, that's where the story ends. The storm dies, the atmosphere resets, the threat passes. But in a double-barrel configuration, the occlusion of the first low creates the exact boundary conditions needed for a secondary cyclogenesis, a new surface low spinning up along the trailing frontal boundary, pulling fresh energy from the warm sector that the first low left behind. The result is something that storm forecasters find both fascinating and deeply inconvenient to predict. Instead of a 1-day or 2-day severe weather window, you get a storm regeneration loop. The severe weather threat doesn't end when the first round of storms moves through. It resets. New boundaries form. New convection fires. New rounds of supercells and squall lines develop on what looks, to an untrained eye, like a weakening system. This is why the Storm Prediction Center is flagging 4 consecutive days instead of 1. This is why experienced forecasters are treating this as a cycle rather than an event. There's a hidden dynamic worth understanding here, because the models have a known weakness with secondary cyclogenesis. They tend to underplay it in the early forecast period. The signals are there in the data, but because the second low hasn't developed yet, because it literally doesn't exist yet. As a physical feature, the models have to infer its development from precursor conditions. When multiple models are all inferring the same secondary development at the same time, that's a high confidence signal. When you combine that with the double-barrel structure and the extended range agreement we already discussed, you start to understand why the forecasting community is treating this weekend the way they are. And we haven't even talked about the fuel yet. Because here's where the setup starts to feel genuinely anomalous, not just in terms of storm structure, but in terms of what the atmosphere is doing with moisture and where it's putting it. There is a body of air preparing to move across the central United States that does not belong there in April. Not even close. The Gulf of Mexico is the source region for the moisture that fuels the majority of severe weather in the United States. During active severe weather patterns, the low-level jet stream acts like an atmospheric pipeline, pulling warm, humid air northward from the Gulf and injecting it into the warm sector ahead of advancing cold fronts. Dew point temperatures, which are the most direct measure of atmospheric moisture content, typically reach the 60s in Fahrenheit across the southern plains during severe weather setups. That's normal. That's expected. That's where the fuel lives. What the models are showing for this upcoming event is dew points in the 60s reaching all the way to Minneapolis. Minneapolis, that is roughly 600 miles north of where that moisture normally stops in April. The climatological boundary, the line that separates the warm, moist air masses from the cooler, drier air to the north, is being pushed so far north by this system that it constitutes what meteorologists quietly describe as a seasonal boundary violation. The atmosphere is being forced to do something that April doesn't usually permit. Here's why that matters in physical terms. When warm, moisture-laden air with 60-degree dew points collides with a deep, cold, mid-level trough, diving southward out of Canada, the thermodynamic contrast is enormous. Warm air is less dense than cold air. It rises rapidly when forced to do so. Cold air aloft dramatically increases the rate at which rising air parcels accelerate upward. That's called instability. When you combine deep moisture, high instability, and the kind of wind shear that rotates thunderstorm updrafts into supercells, you have built exactly the kind of atmospheric engine that produces significant tornadoes, giant hail, and destructive winds. The fuel is not just present, it is displaced far outside its normal range, which means the tornado corridor for this event expands well beyond the traditional zones. States that don't typically see their highest severe weather risk in early to mid-April are going to be on the wrong side of this boundary. And when you combine that geographic expansion with the multi-day storm cycle driven by the double-barrel low, you start to understand why this setup is being discussed, in the terms it's being discussed in. But I want you to hold that thought. Hold the atmospheric architecture, the fuel displacement, the storm regeneration loop, and carry it into the next part, because the violence of what's coming is only half the story. The other half is what happens when the ingredients aren't just present, but stacked. The atmosphere has a recipe for violence. It's not a secret recipe. Meteorologists have known the ingredients for decades, and forecasters use them every single day to assess the potential for severe weather. But knowing the ingredients doesn't tell you how explosive the dish is going to be, because the quantity of each ingredient matters as much as the presence of it. And what this system is bringing to the table in terms of raw quantities is the part that made experienced forecasters stop typing and start paying attention. Start with instability, because instability is the engine of everything that follows. Meteorologists measure atmospheric instability using a value called CAPE, convective available potential energy. The simplest way to think about it is this. CAPE measures how much energy a parcel of rising air can extract from the atmosphere on its way up. Low CAPE means the air runs out of energy quickly and storms stay weak. High CAPE means the air keeps accelerating upward and storms grow tall, organized, and explosive. Values around 1,000 joules per kilogram support ordinary thunderstorms. Values around 2,000 support significant severe weather. For this event, models are indicating the potential for CAPE values between 3,000 and 4,000 joules per kilogram, in some scenarios potentially higher, in the warm sector ahead of the main boundary. That is a highly charged atmospheric column. The updrafts and the strongest storms under those conditions are not metaphorically powerful. They are physically capable of suspending bowling ball-sized hailstones in mid-air and spinning rotating columns of air strong enough to destroy reinforced structures. Now, layer in the wind shear, because CAPE without shear gives you tall, dumb thunderstorms that collapse under their own weight. Wind shear is what gives the atmosphere its organizational intelligence. It's the change in wind speed and direction with height, And when that change is strong enough, it tilts the updraft of a developing thunderstorm away from its own downdraft, allowing the storm to sustain itself for hours instead of minutes. The models for this event are showing deep layer shear values in the 50 to 60 knot range across the primary risk zone. That is classic supercell territory. When a meteorologist sees 50 plus knots of shear sitting on top of 3,000 plus cape, they're not asking whether rotating storms will develop. They're asking how many and where. Then add the low-level jet. The low-level jet stream is a concentrated river of wind that develops in the lower atmosphere, typically overnight, and it does two things simultaneously. It pipes moisture into the warm sector, and it injects low-level rotation into developing thunderstorm updrafts. This event is expected to produce a low-level jet around 45 knots, feeding 60-degree dew points northward while dramatically increasing the potential for tornadic supercells. Think of the entire setup as a mechanical system where you're stacking gasoline, oxygen, and a spark at the same time in roughly the right proportions, in the right sequence. All three ingredients are not just present, they're arriving together. This is where the supercell conversation becomes unavoidable. A supercell thunderstorm is not simply a large thunderstorm. It is a qualitatively different atmospheric phenomenon, a self-organizing, rotating updraft system that can sustain itself for multiple hours while producing all categories of severe weather simultaneously. The rotating updraft, called a mesocyclone, is what creates the conditions for tornado formation, for giant hail growth, for catastrophic downdraft winds. During peak instability in the warm sector, discrete supercells, individual, isolated rotating storms, will likely develop ahead of the main frontal boundary. These are the most dangerous configurations for significant tornadoes because they have room to breathe, room to organize, and room to produce long-track violent tornado events without the interference of neighboring storm cells. I want to emphasize the uncertainty here, because intellectual honesty requires it even when the setup looks this alarming. Not every location under the severe risk zone will experience severe weather. Storm placement, subtle temperature gradients, small-scale atmospheric features that models can't fully resolve, all of these can be the difference between a city seeing dramatic radar imagery 80 miles away versus a city experiencing a direct hit. Forecasting in the 4 to 48 hour range narrows those uncertainties dramatically. Right now, the confidence is in the environment. The specific execution resolves later. But here's the part that adds a layer of complication that a single-day outbreak doesn't have. And this is the piece of the forecast that the double-barrel low makes uniquely challenging to communicate. This is not a one-round event. The forecast calls for multiple rounds of organized convection stretching from Saturday through at least the following Tuesday. Multiple rounds. 4+ days of an active severe weather pattern, with different regions coming into the risk window on different days, driven by embedded shortwaves rotating through the upper level trough and the secondary low reinforcing the surface boundaries. Embedded shortwaves are small-scale energy impulses that travel through the upper atmosphere within the larger trough pattern. They act as individual triggers for convective development, each one capable of lifting air parcels to their level of free convection and igniting new rounds of thunderstorms. Because multiple shortwaves are expected to cycle through the system over this multi-day period, the severe weather threat doesn't just persist, it pulses. You get a round of storms Saturday evening, a lull, a regeneration overnight, a new round Sunday, another lull, another round Monday. This is what storm forecasters call a severe pipeline, a conveyor belt of convective triggers moving through an atmospheric environment that remains primed and ready between each cycle. The forecasting challenge this creates is genuinely difficult. A small timing shift in when a shortwave arrives can shift the primary risk zone by 200 miles. A slight variation in how quickly the warm sector destabilizes can change whether the dominant storm mode is discrete supercells or an organized squall line, and those two storm modes have very different threat profiles. Discrete supercells maximize tornado potential. Organized squall lines maximize straight-line wind damage. The atmosphere will likely produce both across this multi-day window, in different regions, at different times, in a sequence that even the best models will struggle to pin down until 24 to 36 hours before each event. There's a human dimension to the multi-day problem that pure meteorology doesn't capture, and it's worth naming directly. Emergency managers and public safety officials operate on a resource model built around single events. You issue warnings, you position resources, you respond, you recover. A 4 to 6 day severe weather cycle strains that model in ways that a single outbreak doesn't. Communities that take a hit on Saturday night may still be in active response mode when the next round arrives Monday. Warning fatigue is real. It's a documented psychological phenomenon where repeated exposure to weather alerts reduces behavioral response compliance. The multi-day nature of this event isn't just a meteorological complication, it's a compounding societal one. And here's the thing that I think gets consistently lost in the tornado-focused media narrative around events like this, and I say this as someone who finds tornado dynamics genuinely fascinating. The tornado threat is dramatic, photogenic, and terrifying. But in terms of raw geographic footprint and aggregate damage potential, the wind and hail threat from this system may ultimately prove broader in its impact than the tornado headline. Let me explain why. Hail formation inside a supercell requires a strong updraft that can suspend ice particles aloft long enough for them to accumulate mass through repeated trips through the supercooled water zone of the storm. The stronger the updraft, the larger the hail. Under the Cape values expected in this setup, the strongest supercell updrafts will have enough energy to produce hailstones approaching baseball size, roughly 2 to 3 inches in diameter, in the most intense cores. Baseball-sized hail falling at terminal velocity is not a nuisance. It destroys car glass, perforates metal roofing, shreds crops, and injures people. The hail threat extends beyond the immediate tornado risk area and affects a much wider corridor. The straight-line wind threat carries its own separate profile. As the event evolves from discrete supercells into organized linear convective systems, bow echoes, and squall lines, the wind threat intensifies significantly. A bow echo is a radar signature that looks exactly like what it sounds like. A bowed-out line of thunderstorms curving forward at its apex, driven by a concentrated rear inflow jet that accelerates the system's cold outflow. Wind gusts exceeding 80 miles per hour are possible in the strongest bow segments. At those speeds, you're talking about structural damage to buildings, widespread tree failures, and power outages affecting hundreds of thousands of people across a multi-state corridor. If atmospheric conditions and jet stream alignment cooperate over the right geography, the linear convective system could evolve into a derecho, a long-lived, fast-moving wind event that can produce damage swaths hundreds of miles long. A derecho requires a very specific alignment of ingredients and isn't guaranteed in any individual setup, but the conditions being assembled here meet the threshold of plausibility. The tornado threat will dominate the headlines. It should be taken seriously. But when the damage surveys come in days after this event, I'd be willing to bet that the wind reports stretch from state lines the tornado tracks won't reach. That's the hidden architecture of a multi-mode severe weather outbreak. The dramatic story obscures the broader one. And the tornado story, as dramatic as it genuinely is only one of 5 simultaneous weather emergencies currently converging on the continental United States. Here is something that almost never gets said in the mainstream weather coverage of a major plains severe weather outbreak. The rest of the country does not pause while the tornadoes spin. The same atmospheric pattern that is organizing supercells across the central United States is simultaneously producing catastrophic conditions from Florida to California, from the Pacific coast to the Sierra Nevada, all at the same time, all driven by the same underlying atmospheric reorganization. 5 simultaneous weather emergencies, 1 country, 1 connected atmospheric system expressing itself differently depending on the terrain and moisture regime of each region. Start in South Florida, because what is happening there right now is not a preview of what's coming. It is already in progress. A tropical moisture surge has been feeding a persistent plume of very high precipitable water into the Florida peninsula, and the result has been a rainfall pattern that urban infrastructure was simply not designed to handle. The forecast rainfall totals for the most vulnerable areas are in the range of 6 to 12 inches, not over several days, but in concentrated bursts driven by training thunderstorms. Training thunderstorms are exactly what they sound like, a sequence of storm cells that repeatedly move over the same geographic area along the same path, like train cars passing over the same track. The first storm soaks the ground. The second storm fills the drainage systems. By the third storm, the water has nowhere to go. South Florida's drainage infrastructure is already operating at the edge of its design capacity in a normal rain event. The combination of urban hardscape, the impermeable surfaces of roads, parking lots, and building footprints, with an already saturated soil moisture profile, creates a situation where rainfall rates can exceed drainage capacity almost immediately. Flash flood emergency thresholds can be crossed, not because the total rainfall is catastrophically high in an absolute sense, but because the rate of rainfall delivery is faster than water can move through the available channels. This is the flooding mechanism that turns streets into rivers in 20 minutes, and strands vehicles in underpasses that were dry an hour earlier. The deeper issue here is one of compounding rather than single event magnitude. South Florida's flooding problem over the coming days will not be defined by one catastrophic rainfall event. It will be defined by the accumulation of multiple events on infrastructure that never fully drains between them. Each round of heavy rainfall starts from a higher baseline of soil saturation and system capacity utilization. The threshold for flash flood emergencies gets lower with each successive event, not higher. This is a crucial concept that the weather headline machine struggles to communicate. The danger doesn't necessarily peak in the first event. It compounds. Flooding becomes cumulative, not single event driven. Now, shift your attention approximately 3,000 miles northwest, because while South Florida is drowning, the Sierra Nevada mountain range is preparing for a multi-day snow event of a different category entirely. A powerful Pacific system is approaching the west coast, and it is carrying with it an atmospheric river, one of those narrow, concentrated corridors of water vapor transport that occasionally connect the tropics to the mid-latitudes and deliver rainfall and snowfall totals that compress months of precipitation into days. Atmospheric rivers are named with the same casual understatement that forecasters often use for genuinely extreme phenomena. A river suggests something benign, something you can ford if necessary. An atmospheric river carries roughly the same volume of water vapor as 10 to 15 Mississippi rivers, flowing not in a channel, but through the air at altitudes of 1 to 3 miles, in a corridor sometimes narrower than 300 miles wide, but extending thousands of miles back to its tropical moisture source. When that corridor makes landfall against an orographic barrier, a mountain range that forces the moist air to rise rapidly, the result is precipitation totals that compress months of normal climatology into hours. The Sierra Nevada is an extraordinarily efficient orographic precipitation machine. The range rises from near sea level to peaks above 14,000 feet within a horizontal distance of roughly 60 miles. Moist Pacific air with nowhere else to go rises rapidly and deposits nearly all of its moisture content as it climbs. At elevation, that moisture falls as snow. The forecast for this system carries snowfall potential in the range of 3 to 6 feet at the higher elevations over the course of the event, with ridgetop wind gusts potentially reaching 100 miles per hour during the system's peak intensity. To put 3 to 6 feet of snow in 3 to 5 days in context, that is not ski resort promotion material. That is avalanche territory, whiteout conditions, structural load concern for older buildings, and the complete closure of major mountain passes that connect Northern California communities to the rest of the state. The combination of extreme snowfall and near hurricane force ridge winds produces blizzard conditions, where wind-driven snow reduces visibility to essentially zero, and wind chill values push temperatures far below what the thermometer alone would suggest. The same moisture that is fueling the organized severe weather in the central United States is arriving at the Sierra Nevada's doorstep and getting converted by altitude and terrain into something that looks nothing like a thunderstorm, but carries comparable destructive potential. Now, here's the part of this national weather picture that feels genuinely paradoxical, the part that requires you to hold two contradictory images simultaneously. While South Florida floods and the Sierra Nevada buries itself in snow, large portions of the American Southwest and Southern Plains are experiencing fire weather conditions of an entirely different variety. Critical fire weather alerts, relative humidity values dropping into the single digits, sustained winds in the 30 to 60 mile per hour range, fuels, the grasses, brush, and timber that accumulate through dry winters and dry springs, reaching extreme dryness thresholds. The mechanism is embedded in the same large-scale atmospheric pattern, generating all the other hazards. On the western, dry side of the advancing storm system's split-flow structure, very dry continental air descends and accelerates through gaps in the terrain, producing the kind of wind-driven low-humidity conditions that fire behavior analysts classify as critical. On the eastern side of the same system, tropical moisture surges northward and fuels the convective instability, feeding the severe weather outbreak. Two sides of one atmospheric structure, one side drowning, the other burning. This spatial paradox, simultaneous floods and fires driven by the same storm, is not a coincidence. It is a feature of how split-flow upper-level patterns work when they're amplified over continental scales. The downstream ridge on the western flank of the trough compresses and accelerates surface air, drying it dramatically as it descends. The upstream trough on the eastern flank lifts and destabilizes the moist air mass, feeding it northward into the severe weather corridor. Same storm, opposite extremes, separated by a few hundred miles. One atmospheric system expressed in completely opposite ways depending on which side of the boundary you're standing on. And if you're keeping count, we've now accounted for 4 of the 5 simultaneous weather emergencies: South Florida flooding, Sierra Nevada snow, Southwest fire weather, and the Central Plains severe weather outbreak. The 5th is quieter in media coverage, but affects the daily lives of more people than the others. 14 rivers across the Midwest are currently running in flood stage or above. Not flash flood events, but sustained river flooding from a winter and early spring that was already wet before this week's additional rainfall input. The river systems across the Ohio Valley, the upper Mississippi watershed, and the Central Plains are operating with reduced surge capacity. They are already carrying heavy loads, and the runoff generated by multiple rounds of severe thunderstorm rainfall over the coming days will have to go somewhere. The somewhere is downstream river gauges that are already above flood stage, rising toward major flood thresholds, in communities that have been managing high water for weeks. This is the compound hazard structure that no single weather headline captures, and it's the reason the meteorological community's nervousness about this pattern goes beyond any individual element of it. It's not that one of these events is uniquely unprecedented. It's that 5 of them are converging simultaneously, reinforcing each other's consequences through shared infrastructure stress, emergency management resource competition, and, most critically, a common atmospheric driver that connects all of them. and that driver is doing something that requires looking not at the atmosphere, but at the ocean beneath it. Everything we've described so far, the double barrel low, the moisture displaced to Minneapolis, the 5 simultaneous weather emergencies, these are surface-level manifestations of something that has been building in slow motion for months beneath the surface of the Pacific Ocean. Something that hasn't fully arrived yet. Something that, when it does arrive, will reach into every corner of the Northern Hemisphere's weather patterns and alter what we should expect from the seasons ahead. I want to be precise and careful about this, because we're entering territory where the science is real, but the certainty is not. And conflating the two is how misinformation about weather and climate gets manufactured. So let me tell you what we know, and then I'll tell you what the patterns suggest, and I'll be explicit about which is which at every step. The El Niño Southern Oscillation, ENSO, is the most powerful cyclical climate driver on the planet. Not the most discussed, not the most dramatic in name, but in terms of raw influence over global weather patterns, nothing else operating on a 2 to 7 year cycle comes close. ENSO alternates between two opposing phases: El Niño, characterized by anomalously warm sea surface temperatures across the central and eastern tropical Pacific, and La Niña, characterized by anomalously cool temperatures in the same region. The temperature differences themselves sound underwhelming, a few degrees Celsius above or below the seasonal average across a broad expanse of open ocean. You'd be forgiven for wondering how a few degrees of sea surface temperature in the middle of the Pacific could matter to a tornado forming over Kansas or a flood event in South Florida. The answer is that those few degrees don't act locally. They act globally by reorganizing the entire atmospheric circulation of the Northern Hemisphere. The location where the tropical Pacific is warmest determines where the most vigorous convection occurs, where the atmosphere is being heated most intensely from below, where thunderstorm clusters are most persistent, where the rising branch of the large-scale tropical circulation is anchored. That rising branch is connected through a system of planetary-scale atmospheric waves to the descending branches elsewhere, the zones of sinking air that produce clear skies and dry conditions in some regions, and to the position and intensity of the jet streams that steer weather systems across the mid-latitudes. Move the heating source in the tropics, and you move everything downstream of it. The jet stream shifts. Storm tracks shift. The moisture corridors shift. The frequency of certain weather patterns across entire continents shifts. A few degrees in the equatorial Pacific rewrites the atmospheric rulebook for seasons at a time. For the past several months, the tropical Pacific has been transitioning out of La Niña conditions and beginning to show early indicators of a potential El Niño development. The mechanism driving that transition is visible in the subsurface ocean temperature data. A Kelvin wave, a slow-moving pulse of anomalously warm water propagating eastward along the equatorial Pacific at depths of roughly 50 to 200 meters. Kelvin waves are not surface features. You cannot see them from a satellite image of the ocean surface. They exist in the subsurface temperature field, detectable only through a network of moored buoys, Argo floats, and ocean sampling instruments that measure temperature at depth across the tropical Pacific. The wave travels at a speed of about 2 to 3 meters per second, faster than you might expect for an ocean process, but still requiring weeks to months to traverse the full width of the Pacific Basin. Think of a Kelvin wave as a letter the ocean is writing to the atmosphere, a letter composed weeks or months ago somewhere in the Western Pacific, addressed to the Eastern Pacific and the atmosphere above it, currently somewhere in transit across the open ocean. The atmosphere will not receive that letter until the warm subsurface water rises to the surface near the coast of South America and begins modifying the sea surface temperatures that drive atmospheric convection and circulation. But the forecasting models can track the wave's position, amplitude, and trajectory. They can estimate with reasonable confidence when the letter will be delivered and roughly how warm the message will be when it arrives. The current models are indicating that this subsurface signal, when it surfaces, will likely push ENSO into weak to moderate El Niño territory by mid to late summer of 2026, possibly earlier if the Kelvin wave carries more thermal energy than current estimates suggest. Possibly stronger than current estimates suggest, for the same reason. Here is the piece of this that connects directly to what we're watching unfold this week, and it's the piece that most weather coverage completely omits. Early-stage ENSO transitions do not wait politely for the official El Niño declaration before beginning to influence atmospheric patterns. The official threshold, a 3-month running average sea surface temperature anomaly of positive 0.5 degrees Celsius in the Niño 3.4 region, is an administrative boundary. The atmosphere doesn't observe administrative boundaries. The warming Pacific, even before sea surface temperatures cross that official line, begins shifting the position of the Pacific jet stream, altering the steering currents for North American storm tracks, and enhancing the moisture transport from tropical source regions. The atmospheric response can precede the oceanic threshold by weeks or months. Some climate researchers describe this as the atmosphere sensing the coming ENSO state before the ocean fully delivers it. Whether that framing is precisely mechanistic or somewhat poetic, the observational record is broadly consistent with it. What we appear to be watching in the current spring pattern is a jet stream configuration consistent with an early ENSO transition signature, amplified trough ridge patterns over North America, enhanced moisture transport from anomalously warm subtropical waters, a stronger than typical meridional flow, meaning the jet stream is not moving in a relatively straight west to east track, as it tends to do during neutral ENSO conditions, but is instead carving large north-south waves across the continent. Those waves are what punch moisture northward well beyond its normal seasonal boundary, creating the displaced dew points we discussed earlier. They're also what allows cold air from polar regions to dive southward on the other side of the trough, creating the thermodynamic contrasts that make severe weather environments explosive rather than merely active. These are not independent anomalies happening to coincide this week. The Sierra Nevada atmospheric river, the South Florida tropical moisture surge, the 60-degree dew points reaching Minneapolis, the fire weather on the dry side of the system, the 14 flooded rivers. They are all expressions of the same underlying large-scale atmospheric state. And that state has a Pacific fingerprint. The question is how deeply that fingerprint goes, and how long it persists. I want to be explicit about the limits of this connection, because intellectual honesty requires it even when, especially when, the pattern looks compelling. Attributing any specific weather event to ENSO transition dynamics is scientifically complicated in ways that public weather communication rarely acknowledges. The atmosphere is a chaotic system. Small perturbations produce large consequences. Large-scale forcings, like ENSO, modulate the probability of certain atmospheric configurations without determining them. We cannot draw a direct causal arrow from a subsurface Kelvin wave in the equatorial Pacific to a double-barrel low-pressure system over the Central Plains to a tornado touching down in a specific county in Nebraska. The chain of causation passes through too many nonlinear steps, too many sensitive dependencies, too many places where the butterfly effect can redirect the outcome. What we can say, and this is a meaningful scientific statement even if it sounds cautious, is that the pattern of the atmosphere over the last several weeks is consistent with what early ENSO transition often looks like in North American spring patterns. Consistent with is not the same as caused by. Keep that distinction in mind, because the people who will tell you otherwise exist on both sides of the argument, and neither of them is being straight with you. What is somewhat more tractable, more amenable to direct analysis, is the concept of stacked anomalies. Multiple atmospheric and oceanic parameters simultaneously pushed in the same direction, amplifying each other's effects rather than canceling them out. Sea surface temperatures across the subtropical Pacific are running above their seasonal averages. Sea surface temperatures in the Gulf of Mexico, the primary moisture source for severe weather in the United States, are running above their seasonal averages. The global mean sea surface temperature has been running at record or near record levels for well over a year, a streak that has attracted significant attention in the oceanographic community for its persistence and magnitude. An anomalously warm ocean surface does not conjure weather events from nothing. The atmosphere still needs the right dynamical setup, the right jet stream configuration, the right surface boundaries, the right upper-level forcing to organize a significant storm system. But a warm ocean loads the dice. When the atmosphere reaches down for moisture, there is more moisture available to pull up. When a storm system tries to intensify, it has access to more thermodynamic energy from the ocean surface below. The amplitude of what the atmosphere can do, when it gets the right setup, is elevated above what the same setup would produce against a cooler ocean background. When you stack warm oceans, enhanced moisture transport, an amplified meridional jet stream pattern, and the early atmospheric response to an ENSO transition signal, you create what some meteorologists describe informally as an overcharged atmosphere, an atmospheric state where the available energy for weather systems is running above typical background levels, not infinitely, not catastrophically, but measurably and consequentially above the seasonal climatological baseline. The analogy that feels most physically accurate is resonance. When you push a pendulum or a swing at exactly the right frequency, each push adds energy to the system, and the amplitude of the oscillation grows. You don't need enormous force. You need the right timing applied repeatedly. The current atmospheric state appears to be hitting something like that resonant frequency, each storm cycle drawing from the same enhanced moisture and energy reservoirs, each system modifying the boundary conditions in ways that prime the next system. The atmosphere amplifying its own output through a self-reinforcing sequence of events. How long that resonance persists before the pattern breaks down and resets is one of the central questions that extended range forecasters are currently trying to answer. The honest questions, the ones worth sitting with, are these. Is what we're watching simply natural variability expressing itself at the outer edge of its normal range? The atmosphere has always been capable of producing compound multi-hazard events during active spring pattern regimes. Multi-day outbreaks, simultaneous regional disasters, amplified moisture transport, none of these are new phenomena. The historical record contains examples of all of them. Or is this pattern an early signature of an ENSO-driven atmospheric regime that will persist and potentially intensify through the peak of severe weather season? Is the relationship between anomalously warm oceans, ENSO transitions, and amplified spring storm patterns something that is merely becoming more visible as our observational networks improve, or something that is genuinely shifting in character and frequency in ways that the historical record from earlier decades didn't prepare us for? These questions do not have clean answers right now. Atmospheric scientists and climate researchers are actively working on exactly these attribution problems, and the honest state of the science is that it is unresolved. The uncertainty is real. Anyone who presents confident conclusions in either direction, either confidently dismissing the Pacific Connection or confidently asserting a direct causal chain, is overstating what the evidence currently supports. What I can tell you with confidence is what the data shows right now, in this moment, in this specific setup. The atmosphere is organized for a significant, multi-day, multi-hazard severe weather event affecting large portions of the continental United States. The pattern generating that event carries signatures consistent with Pacific Ocean atmosphere coupling in an active transitional state. The compound nature of the simultaneous hazards, tornadoes, flooding, blizzard conditions, fire weather, river flooding, suggests a large-scale atmospheric state that is not producing isolated regional events, but expressing a coherent, high-energy configuration across the entire continent simultaneously. That configuration has a source. That source has a Pacific fingerprint. The depth and duration of that fingerprint is what remains uncertain. And here's the part that should genuinely give you pause, if the rest of this hasn't already. Spring severe weather season in the United States typically peaks in late April through May, in some years extending into June across the northern tier of the country. This event, significant as it is, as alarming as the forecaster consensus around it has been, arrives at the early edge of that peak season window. We are not in the middle of severe weather season. We are at its beginning. The atmospheric pattern that is generating this week's compound hazard environment will not permanently reset after Tuesday. The double-barrel low will eventually wind down. The moisture will temporarily pull back south. The immediate severe weather boundaries will shift and weaken. But the ENSO transition continues moving forward on its own timeline, indifferent to our weather events. The Pacific remains anomalously warm. The jet stream remains in an amplified meridional configuration. The same recipe that assembled this week's environment will have opportunities, multiple opportunities, to reassemble across the weeks ahead, potentially with a stronger Pacific signal underneath it each time. Which brings you to the question that responsible meteorology frames carefully, and that responsible journalism mostly avoids entirely, because it doesn't fit neatly into a weather alert or a breaking news banner. If this is what early season, early ENSO transition atmospheric conditions can produce, 60-degree dew points at Minneapolis, 5 simultaneous weather emergencies from Florida to California, 4 consecutive days of extended range severe outlook highlighting a multi-day storm regeneration loop, then what does peak season look like when the El Niño signal has fully surfaced? When the subsurface Kelvin wave has delivered its thermal payload to the eastern Pacific and sea surface temperatures have crossed the official threshold? When the jet stream has had another 6 weeks of amplification? When the moisture source feeding these systems is not merely warm, but anomalously warm through the full depth of the tropical Pacific water column? Nobody knows. That is the correct and complete answer, and I will give it to you plainly, without wrapping it in false comfort. Because the alternative, pretending the uncertainty doesn't exist, is a form of dishonesty that this topic doesn't deserve. Forecasting at seasonal timescales involves uncertainties that are categorically larger than the uncertainties in the extended range severe weather outlooks we discussed at the beginning of this video. The atmosphere is not obligated to follow the ENSO playbook precisely. Individual seasons routinely surprise even the best long-range forecasting systems. History contains El Niño springs that were active and El Niño springs that were not, and the difference between them often comes down to factors that resolve only weeks before the events themselves. But here is what the atmosphere does not care about, not even slightly: what we predicted. It does not smooth its behavior to match our models. It does not produce fewer tornadoes because the media already covered a major outbreak earlier in the season. It does not reduce its moisture transport because the public has already absorbed a lot of severe weather news this spring. It does not time its peak activity conveniently around our warning fatigue or our emergency management resource cycles. What the atmosphere does is follow the physics, the thermodynamics of air masses with different temperatures and moisture contents colliding along boundaries, the fluid dynamics of rotating systems, intensifying in environments with the right wind shear, the boundary conditions imposed by the oceans and the land surface, and the incoming solar radiation that drives the whole system. Right now, the physics are being fed by something building beneath the surface of the largest ocean on the planet, moving eastward at 2 to 3 meters per second, carrying a thermal anomaly that hasn't fully arrived yet and won't for months. The letter is still in transit. The atmosphere is already reading it, or at least reading the return address, sensing what's coming before it fully arrives. And everything we've watched unfold this week the consensus compression event among every major forecaster, the double-barrel low structure, the moisture reaching Minneapolis in April, the 5 simultaneous disasters spanning the full width of the continent, the overcharged atmospheric state running on an elevated energy baseline. All of it may be less the story itself than it is the opening paragraph of a much longer document that the Pacific Ocean is still writing. The season ahead will tell us how many pages that document contains. The question, as it always is with the atmosphere, is whether we're paying close enough attention to read what comes next before it arrives at the door.